we remember from yesterday. So it says, graph the inequality y is greater than negative 1/2 x. Let me ask you this. With these inequalities, we've graphed a lot of lines where it was y equals things like 1/2 x. But with these inequalities, what are the two features that are kind of new once we throw inequalities in there? Well, yeah, Ashlyn. Say again?
What kind of line is it? It's like if it's a dash or...
There you go. Dashed or solid line, right? So that's going to come into play here, and that's definitely one of them. What's the other one? What else comes into play with these inequalities with lines? The dashed line or the dotted line is one of them. You guys going to let Ashlyn dominate you like this? Go, Ashlyn. And how do we usually represent the region? Shading, yeah, little shadings, right? You guys remember that? We did, I think, 3 of them or 4 of them yesterday. We shaded on either side of the line. Ashlyn, thanks for contributing to our class today. Number 4 is kind of like this one. So it says y is greater than negative 1/2 x. Wouldn't it be fair to say that yesterday we used slope-intercept quite a bit?
Yes.
Is this one right here set up for slope-intercept, or should we do some more work to get it there?
We should get it into point slope.
I don't think so. I think it's already in slope-intercept, isn't it?
Oh.
I think it's already pretty well set up for us to just use that. I mean, we could actually do a point slope here, but I think I would rather do slope-intercept because it's already in slope-intercept. Say again? Yeah, I agree. That's why I think we should do it that way. So let's remind ourselves, slope-intercept is y equals mx plus b. So if that's the case, Cole, what is my slope for this particular line?
Negative 1/2.
Negative 1/2 is definitely the slope. Agreed. What's the y-intercept? This one seems to be maybe a little more of a mystery. Victoria?
0.
It's 0, right? Because plus b, there is no plus anything. So the y-intercept is 0. So when you're graphing these, do you start off by plotting the slope out, or do you start by plotting the y-intercept?
Y-intercept.
Always the y-intercept first. I agree. The y-intercept is right there at 0. So I'll just put a dot right there, put my point right there. And then the slope is the normal counting it off, rise over run. So negative 1/2, I would say that negative 1/2 should look something like this. Down 1, right 2. There's a point. That's a point right there. And then we could go down 1, right 2 again. We could also go up 1, left 2. That would be the same pattern. So you could do that if you want. I'm just going to leave it at that. How many points do you really have to graph? How many points define a line? 2. So I really only have to graph 2. I decided to graph some extras just because. Now, once I have plotted those points with you, right? Once I have plotted those points, flip over to that other page there. There you go. Looks like you already did it. Once I've plotted those points, I need to connect those points with either a solid line or a dotted line, like Ashley mentioned earlier. What do you guys think? Should this one be dotted or should it be solid?
Dotted.
Why dotted?
Because it doesn't
Not greater than or equal to, it's just the greater than.
Yeah, we're missing the or equal to part. So if you remember, if the or equal to is there, it's like trying to tell you there's a solid line. If the or equal to is not there, it's like trying to tell you there's little spaces in the line. So I'm going to try to represent that up here. So let's see here. Actually, let's go with this. So here is my attempt. At my line, something like that. Right now it's solid, so I am going to try to make it dotted. There is my dotted line. Do you see it? Okay, so we've covered the first thing that Ashlyn mentioned. We've decided, as you guys correctly did, that this is a dotted line. We got to decide shading. And do you remember how yesterday how we decided where to shade? What did we do?
You plug in like 0, but since this one's on 0, you can plug in like 1 or 2.
Well, so hold on. So Sadie, raise your hand really quick. Do you agree with what Grace has said so far? Yeah. We typically, but she said we plug in a 0. I actually disagree with that. We didn't just plug in a 0. What did we plug in? Sadie?
We plugged in a 1 and then the same number, so they cross out each other.
So like a 1 and a 1?
Like 1 and 1/2 maybe.
I personally would prefer to avoid fractions if I can.
Okay, then just like 1 and maybe like a 2 or something.
Interesting. Yeah, I kind of agree with you. Listen, what kind of thing am I plugging in? Garrett?
Like coordinates that aren't on the line.
A coordinate, like a point, right? So like when you said a 1 and a 2, were you thinking 1 comma 2?
Yeah.
That's what we want to do, right? So some kind of a point that's not on the line. Garrett threw that in there at the end, and that's a very good point. And I think what Grace is trying to say is we normally plug in 0, 0, don't we? 0, 0 is the easiest one to plug in, but we're going to have an issue with this, and it kind of goes to Garrett's point. The issue with this, if I try to plug in 0, 0, where is 0, 0? It's right on the line, isn't it? So that's not really going to tell us what we want to know. I need to pick a point to test over here somewhere or over there somewhere, and that'll tell me where I need to shade. That make sense? Okay, so let's pick. What should we plug in? 1, 1. Okay, 1, 1 is a smart point to plug in, so let's do that down here. So here's our test for this. So I'm going to plug in 1, 1 as you suggested. So y is 1 is greater than negative 1/2 times 1. So this is saying that 1 is greater than negative 1/2. And now we have to decide, is that true or is that false?
It's true.
Totally true, right? 1 is bigger than, 1 is greater than negative 1/2. So that means the region that contains 1, 1 is our region. Wouldn't it be fair to say then that our region, the one that contains 1, 1 is this region right here? Does that make sense? And I think the reason I could say that is because 1, 1 is right there. So since 1, 1 produced a truth, we shade that region. If 1, 1 produced a false, we'd shade the other region, right? We'd shade the other one because if one region is false, the other one would have to be true. One exception to that is if you graph the line wrong. If you graph the line wrong, then yeah, everything else might be off. So be careful with that. But that would be our answer. Like really the picture is the answer. The graph is the answer. There's not really a numerical answer of like x is greater than 2 or y is less than 3 or whatever. It's always going to be some kind of a graphical answer. All right. So is that pretty good? Are you remembering this all right? Seems like you are. I'm encouraged. Why don't you guys try the last two on your own? These are some somewhat unique lines. And let's see how it goes for you. So flip ahead to numbers 5 and 6. So there's number 5. There's number 6. We'll try those out. I'll show you those solutions in a minute. But if you would, please take a minute and try both of them with your partner. Okay, table partners.
All right, big fella.
So for number 5, it says graph the inequality. And as I walked around, there was a pretty high percentage of us that really desperately tried so hard to make number 5 look like this. We really wanted it to be y equals mx plus b. Let's just be really honest with ourselves. X is greater than or equal to negative 2 could, listen, I'm going to say a really strong word here. It could never be written as y equals mx plus b because there's no y. There's no y in there, so there is no way for us to write this as y equals mx plus b. So here's what I'd want you to think of. If you can think of a better illustration, that's great. I'm going to go back to the ski thing. There's 3 scenarios in skiing. One in which you are bored, one in which you are having fun, and the other one where you are not surviving. Okay? So here are the 3 scenarios. If you have a horizontal line, my question would be, why would I bother? So a horizontal line will only have a y variable. No x's, only a y. So why would I ski it? It's horizontal. Ugh, boring. Get it? Now, you could have a slanted line like this, and this would be the one where you might have some fun, right? So a slanted line will have a y and an x. It'll have both variables, y and an x. This will always be a slanty line, and this would be like slope-intercept form, right? Now, the other scenario is the one in which we probably don't survive. If I tried to ski a vertical line, I would get x'd out. So if a linear equation has only an x and no y, it will be a vertical line. If a linear equation has only a y but no x, it will be horizontal. But if the linear equation has a y and an x, it'll be some angled slanty line. Make sense?
Yes.
So when I look at number 5, I see only an x, so I think to myself, oh, if I tried to ski that, I'd get x'd out. It's vertical. So it is a vertical line, and I want to be really clear about this. It is a vertical line at x equals negative 2. So I'm going to find x equals negative 2, which of course is right there. I am going to then draw a vertical line at that spot the best I can. Something like that. There's my vertical line. Does this vertical line need to be dotted or does it need to be solid?
Solid.
Solid because of the or equal to, right? The or equal to is there, so we go solid with this. And then finally I need to test out, am I going to shade the right-hand region or am I going to shade the left-hand region? Normally we plug in a point like 0, 0, right? But there's only one input here, right? There's just an x. And so I can really only input for x. I still am going to test out 0, 0 over here, but I can really only plug in the 0 for x. So 0 is greater than or equal to negative 2. Is that true?
Oh, yeah.
0 is bigger than negative 2. And so 0, 0 is part of my answer region. And so I would answer with that. Over here, I'd shade that right-hand side. All of the points over there should work. And if you think about it, aren't all of the x-coordinates in that region bigger than negative 2? No matter which point you pick, all of the x-coordinates will be something bigger than negative 2. So that would be my answer for number 5. Any questions? Okay. Oh, question, yes.
For the web aside, if you don't shade it, is that considered wrong?
Yeah.
Okay, that's probably what I was.
Yeah, if it's an inequality, you have to shade, because really your only answer is the graph. So if your graph has any issues, they're going to be like, no, sorry.
Okay.
So.
I think that's what I was.
Okay, we can still discuss later if you want, but that hopefully that's it. You can fix that pretty easily. Okay. All right, and then number 6. Try this inequality again. Just want to emphasize to you that this is a horizontal line. Get this. There's plenty of folks that didn't get this. This is a horizontal line. It is not y equals mx plus b. In fact, I will go on to say that there is absolutely positively no way to write this in y equals mx plus b format. I mean, there's one little caveat to that. Because what's missing? There's no x. I mean, you could actually say maybe it was a 0x, but that's not really going to help us. It's still 0. So this is not a slanted line. There is not a y and an x. So you look at it and say it's not a slanted line. Is it vertical or is it horizontal? Well, since there's only a y, you would say, why would I ski it? It's boring, right? It's just going to be flat. I'm going to go 0 miles an hour. It's not going to be any fun. I'm not going to die, but I'm not going to have any fun either. Right? I want to find that happy medium between the two. So this is horizontal. It is horizontal at 4. So 1, 2, 3, 4. So my line would look like, something like that. However, is it solid or dotted? We always have to answer that question. It's dotted. Why is it dotted?
Because it doesn't have an equal to.
The equal to is missing. Yeah, I agree. So I'm going to go through here and just try to make that as dotted as I can. Something like that. There's my dotted line. And finally, to come full circle back around to what Ashlyn said at the start of our class, we need to shade, right? We decided the dotted solid thing. We got the line right. Am I going to shade above or below? So I usually test out 0, 0. Sometimes it works, sometimes it doesn't. Did you test out 0, 0? Does 0, 0 work? Does it create a truth? I think so. If I try out 0, 0 into this, the y-coordinate's 0. 0 is less than 4. That is true. So that means 0, 0 is part of my answer region. So I need to shade that part. So I'm going to shade down there. So that means that any point that I could pick down there, bless you, the y-coordinate will be less than 4. So again, the answer is your graph. We're not going to come up with a singular numerical answer. It'll always be the graph. Nice shading coal. Okay, how are we doing? Have any follow-up questions at all? Okay. Good. Take a look at this right here. Function is a relation in which every input has exactly 1. There you go. 1 output. Not at least 1, not more than 1 or less than 1, but exactly 1. That's the definition of what a function is. Every input, and inputs are represented by x, has exactly 1 output in the range. That makes it a function. So I want to make sure you guys had that. The domain is all your x values, all the okay x values, and your range is all the acceptable y values. Okay, so we'll go a little bit deeper with that here in just a second. So I wanted to do a couple of examples here with you. You had to find the domain and range there at the end of the video. Again, for those that are deciding to not watch the video, they're usually less than 5 minutes if you just watch them straight through. And if you watch them on like 1.5 time, they're even less than that, right? So strongly encourage you to be doing that. We are not going to do a quiz today. Could do a quiz anytime I want, but I'm not doing one today. So let's take a look at here at these examples. I'll do maybe one of them with you, let you guys kind of work through some other ones, just kind of see how it goes. So the instructions here say, determine whether each relation defines y to be a function of x. In other words, another way to ask this question would be, which of these pictures represents a function and which of them does not? So let's take a look at A right here. So notice what's listed in this picture. I want to kind of pick this apart. Did you guys see that over on the left, you got that little oval, but then above it says x's. And on the right, you got another little oval, and above that it says y. That means that the left oval represents your domain or your range. The left oval is which one? The domain or the range? Domain, yep. So the left oval is the domain, and the right one is the range. This is a typical arrangement for these. And this is simply asking us, is this mapping representing a function? So did you notice the little arrows going from each number to other numbers? So for instance, 7 maps to 4. You see how 7 points to the 4? That means if the input is 7, then the output would be 4 for one of these linear functions. If the input is 9, the output is 6. You plug in 9 for x, you get out a 6 for y. We have no earthly idea what the function is at this point. If it's linear, we could probably figure it out, but we just have all these inputs and outputs listed. So the question is, does this represent a function or not? Remember, the definition of function is a relationship in which every input has exactly one output. So that's what we're going to use to decide. How many outputs does the 7 have? 1. It happens to be a 4, but it has exactly one output. How about the 9? How many outputs? Yeah, it maps to a 6, and that's it. How about the 11? How many outputs for that one?
1 is to the 2.
So we would say, yes, it is a function. Let's see here. Why don't you guys, I'll tell you what, let's skip around just a little bit here. Why don't you guys try D? Same question. Is it a function or not? Why don't you guys try D real quick and decide, does D represent a function? Notice it's the same format. You've got your domain on the left. You've got your range on the right. The little arrows mean the same thing. That sort of deal. Please spare us the whistling. Victoria, your question?
Oh no,
Okay, cool. Let's let everybody kind of think that one through.
D would not be because this one has 2 outputs. This could be because it has one. No, because they all have 8 as the end. This can't be a function, right?
Go back to the definition of function. A function is a relationship in which every input has exactly one output. So how many outputs does 0 have?
1.
What about the 3? How about the 4? How about the 9?
Yeah, but if you put them in
They all have
circle thing.
Oh, well, we'll talk about that in a second. The fact is, each of those inputs, and your inputs are 0, 3, 4, and 9, right? Each of those inputs has exactly one output. Now, they happen to all be the same output. I agree with you, that's a little bit odd. But they all the inputs have exactly one output.
Is it if the domain's the same one, then they can't be?
Because I could have sworn
So if
last
you
time
had-
I learned that like
So
you can't do that.
So if you have 2 points listed like that, and you have 2 domains that are the same, and they map to 2 different outputs, not a function.
Oh, maybe that's what
I think maybe that's what you're thinking of. Okay, so letter D. Letter D, did you guys decide yes, it is a function, or no, it is not a function? No. The answer is no. The answer is no. Let's talk about why. It's a pretty simplistic strategy, but I think it's a good one. How many outputs does the -1 have? 1. Has exactly one output. There it is. It's a 5. How many outputs does the -2 have? 1. It's a 0. And doesn't the -3 have the exact same output? Yeah. But the -3 still has one output. How many outputs does the -4 have? 2. It outputs to 6 and 11. So that means for the input of -4, it does not have exactly one output. It has 2. And 2 is not 1. And so therefore we could say not a function. Functions are very important. Not everything is a function, but functions are important. Okay, letter B, presented differently. We can still do it though. With letter B, here are all my inputs on the left, 2, 5, 2, and 6. So this one might be a little trickier. Let's go through and ask ourselves, how many inputs does each, or how many outputs does each input have? So how many outputs does the 2 have?
1.
Okay, so 2 maps to 3. How many outputs does the 5 have?
1.
1. Oh my goodness, did you see what comes next? Isn't the, hey guys, hey, those of you who are just chatting, listen. Isn't the 2 listed as an input twice? Okay, now look at it up here. In the top, the 2 had an output of 3, but down here the 2 has an output of 1. And I think, Grace, this might have been what you were getting at. How can the 2 have an output of 3 and an output of 1? Doesn't that mean that the 2 has 2 outputs? So what's our conclusion? Not a function.
Even
Okay.
if they're two separate twos.
Yeah, because 2 is 2, right? So it's saying that you plug in the 2 in one scenario, you get a 3. And you'll see this actually when we start dealing with something called quadratics and other various different graphs. Sometimes you'll plug a 2 in one situation, you get a 3. You plug it in another situation, you get a 1. Makes it not a function.
If it was a negative 2, wouldn't it be?
Yeah, that'd be fine. Yeah, because negative 2 is unique from 2. Okay, then C. And this is the one that we were talking about a little bit over there. All of your domains are listed first, right? Because the domains are x's. So 0 is a domain, 3 is a domain, 4 and 9. Those are all parts of the domain. Excuse me. So I would just ask you, are any of the domain members listed more than once? There's a 0, a 3, a 4, and a 9. I would say that they're all listed as unique domain members. There's no repeats. And so the 0 has an output of 8. The 3 has an output of 8. The 4 has an output of 8, and so does the 9. They all have the same output, but don't all the inputs have exactly one output? So the answer is yes, a function. Sorry, Hosanna.
It's okay.
Stand right smack in front of you there. If we wanted to map this one out, letter C here, here's what it would look like if we mapped it out like we did with those other mappings. We would have 0, 3, 4, and 9 as our domain. And what would be in the range? 8. Just one number, and all of these would map to the 8. They all map to the same output, but not different outputs. Doesn't really matter. They all have one output, makes it a function. All right, how'd you guys do?
Good.
Any questions? Hosanna?
No, I got
Are you sure?
Yeah.
Okay. Anybody else? Sorry about that. Thought or comment? Tight quarters in here. Okay. So let's keep moving here. Let's take a look here at function notation. This is often a new thing. So let's take a minute. This is kind of some vocabulary and terminology. So here we go. If you see a notation like this right here, y equals f of x. Have you guys ever heard of that? Have you ever seen that notation? F of x. If you see y equals f of x, that means y is a function of x. In other words, for every input for x, there's exactly one output for y, just like we were practicing. Function experts, let's go. So in the very recent past, we looked at stuff like this, right? Y equals 3x minus 4, and that is totally valid, 100%, right? We've done this many, many times. However, we're going to look at things a little bit differently at times now. If y equals f of x, then instead of writing y equals 3x minus 4, we might write something like this right here. F of x equals 3x minus 4. And this has the same meaning, really, but there's maybe a little bit of a deeper meaning we can use, too. I can never remember when this class ends. It's changed from last year, and I always mess myself up. So let's talk about these parts and see what we can do with them. So the f in here. The f is simply the name of the function. F is the name of the function. We could have other functions named g of x, h of x, n of x, p of x, y of x. I mean, it could have all sorts of different names, and sometimes they'll have a very specific meaning. The x, as you might expect, this is just telling us what the input is. So the name is f, the input is x, and then 3x minus 4, I'm gonna call that the rule for the function. What I mean by that is the rule for this specific function is this. Take your input, multiply it by 3, and subtract 4. If you saw this in middle school, they might have talked about this like a function machine. Maybe even your middle school teacher like had this little fake machine and they're like beep, 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 beep. You turn the crank, it makes all these sounds. You put in a 5 and it goes through the function machine and out drops a 10, right? So the 3x minus 4, that's like the machine. That's the thing that does the stuff to the input, right? So I'll give you an example of that. If we want to middle school this up a little bit, I'm fine with that. Like if I had this right here, here is my machine. Here is my input for the machine. Here's my output for the machine. This is, and there's like little gears and ropes and pulleys and whatever, who knows, there's some levers and stuff like that in the machine. Who knows what's in there? And so this is the f of x equals 3x minus 4 machine. Like that's the name of the machine. And what you could do is you drop numbers in, right? They're the input. So maybe we decide we're going to drop a 5 in there. We've decided to put a 5 into our machine, and you drop it in there and you push the button. There's the button, and it's beep, 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 gears grinding, and all this stuff happens inside there, and makes this noise. And as this number 5 travels through this machine and does whatever it does, what would happen to it? What would come out on the other end of the machine? Come on, it's the 3x minus 4 machine. I put a 5 in there. 11, right? So the machine did its stuff. It did 3 times 5 is 15, minus 4 is 11. So I dropped in a 5, and beep, 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 beep. The machine does its thing, and out comes an 11, right? Does that make sense? It's refreshing your brain for middle school a little bit. So I'm not going to do the function machine noises every time, but I just wanted to connect that with you, maybe what you'd seen in the past.
I've never seen that.
Did you like my machine noises?
Yes.
Sweet. Cool. Okay. One little note here, and then I think I'll show you one example. Oh, I'm sorry, Jake, go ahead.
So when you put in the 5 for x and you got 11, how do you know, which to put, where to put 5 for which x?
Both, actually.
Both.
Yep, I'll show you that in a second. Yep, it goes in for both. Because literally, if it's an x, like we were talking about, a 2 is a 2 is a 2, an x is an x is an x. If it goes in for one x, not only should it go in for the other ones, it has to. It absolutely has to. So let's take a look here. One little note here, then I thought I'd do one example. And this is a really important note. No, guys, this is the number one mistake conceptually with these questions. It is this. It is mistaking the meaning of the notation. Sometimes people will think that f of x, like f parentheses x, sometimes people think that that means f times x. It does not. And this might somewhat go to Jake's point earlier. F of x is a notation that means the name of the function is f and the input is x. It does not mean f times x. It's really important that we get that notation. And this, to be honest with you, this is at the same level as, like when you were back in, preschool even, when maybe your parents or somebody said, hey, you know what? This is the letter A. At the time, you might have said, why? Why is that an A? And you can see now that's like sort of an invalid question. It's like there is no why. Like we've just all agreed as English speakers that that's called A, right? And so for somebody to be like, well, why is that an A? There might be some like deep historical meaning to why is that an A. But on the surface, don't we just say it's just an A, right? Just accept it. At the same level, this is sort of the same level, right? So F, listen please. F parentheses x or g parentheses x or h parentheses x, whatever the name of the function is, it does not mean f times x. It just means the name is f, the input is x. That's all it really means. So please don't confuse the two. Let's do one example here and then we'll call it good for the moment. So number 3 says, guys, we just bought a brand new function machine. Did you see it? We just bought a brand new function machine, and it makes different beepy beeps. And, well, it's right here. Look at that. I saw it. The name of our, then we had that other function machine before. It's outdated now. We came up with a brand new function machine that we just bought. This new function machine is called f of x equals negative 5x plus 7. It's got new features. It's got a negative 5. Ashlyn, did you see it? Gracie, did you see the plus 7? Oh my gosh, it's all put together so nicely. Do you see our machine? Sorry if I scared you. Wow, look at this. Now, we just got our function machine. We brought it home. We're all so excited about it. What is the very first thing we're going to do with our function machine? Look at the next line down. What are we going to do with it?
Plug in.
We're going to plug in a 3. Are you guys excited? This is better than a new Xbox or whatever it is you like. Kind of is an Xbox. There's an X in the box, right? Yeah. You see it? Yeah. Yeah. Okay, so here we go. It says find f of 3. So here's what that's telling us. I kind of made a little joke about it, but let's be a little more serious. F of 3 means we need to plug a 3 into our function machine. We need to drop a 3 in there. So f of 3 would be f of 3 equals negative 5 times 3 plus 7. I just replaced the x with 3. Let's remember now that f of 3 does not mean multiplication. It just means the name of the function is f and the input is 3. So we do a little bit of work here and we say, do a little arithmetic. Negative 5 times 3 is, and then plus 7, beep, beep, beep. You know, function machine noise is, yep, negative 8 is what came out of the machine. We dropped in a 3 and we got out a negative 8. Okay, so that's what our function machine is. And we just happily use that. I'm really excited about that. Tongue in cheek, I get that. But if the input is 3, the output is negative 8. And guys, this is where we stop. This is the end right here. This is saying if the x was 3, then the output, the y, is negative 8. If the input is 3, the output is negative 8. We don't do any division. Why wouldn't we do any division here?
Because there is no.
Because there's no multiplication happening, right? It's not f times 3. It's f of 3, so there's no need to divide. We're not solving for f or anything like that, because you really can't. It's f of 3 equals negative 8. Okay, hope that worked for you guys. We'll do some more practicing with this mañana. Great job.